So today I am going to talk to you about machine learning and automated ML. So let's dive in. In this lecture, we are going to dive deeper into machine learning and understand the concepts behind machine learning models. Also, you will see how we train models to carry out complex tasks by observing historical data and tuning parameters to do this with high accuracy. Now, as an AI product manager, you're always looking to develop AI products, and it is important to understand the mechanics of machine learning. Model architecture, training data, and model evaluation are all key elements of ML and are instrumental in successful AI product management. When using AI and products, there are numerous uncertainties that can alter the course of development, and by understanding these core concepts, we can stay ahead of the unknowns and plan development accordingly. The concepts in today's lecture will cover various aspects of machine learning, some more technical than others. These topics are meant to give you a peek under the hood of ML and get familiar with some of the components. When building AI products, you are likely to interact with experts in the field, and knowing some of the lingo will definitely help you become more effective when managing these products. So let's get started. So here are the concepts that we will cover in this lecture. We will start with looking at the actual models used in machine learning and understand the components that make up this technology. Next, we'll talk about the training data, and we'll see that how training data serves as examples from which machines will learn subsequently after training any model, and we will see the need to understand the model's performance. And then we'll follow with the discussion of model evaluation and what key metrics we want to measure to understand how our model is likely to perform in production. And finally, we'll talk about transfer learning, a core concept in modern day machine learning that allows us to bootstrap models and achieve robust performance relatively quickly, and as well as automated ML, which has made machine learning more accessible to individuals looking to develop performance AI without requiring a PhD in data science. So, with that said, let's dive into the first section. Modeling and machine learning consists of constructing the core components that will serve as the framework for a machine learning model. So now let's take a look at the term neural networks and what that actually means. So we are going to take an example. Say you need to make a decision. Should I go to a work colleague's party? Neural networks could be deployed to help you make that decision. So a neural network makes decisions based on weighing evidence. The inputs are yes-no questions. The output is also a yes-no question. So you could have three inputs such as am I free? Will it be fun? Is it near public transit? The outcome of those three questions gets you to a more global decision output. Unfortunately, life's a little bit more complicated and some things matter more than others. So this is introducing the concepts of weights and thresholds here. So in this case, am I free? If we've given that a weight of 6 and the threshold overall for making this decision is 5 or above, it really only matters if you are free, because will it be fun has a weight of 2, and is it near a public transit also has a weight of 2. So basically, if you are free, no matter what, you are going to go to that party. However, if you change the threshold to B7 or you change some of the weights around, multiple factors would contribute into whether or not you are free. It also has to be fun or near public transit. What's really important here is that as a good AI product manager, you have to make sure that your data science team or your machine learning team really knows all of the data that's going to be critical for making this decision. Are these factors the only factors to consider? Perhaps you also might want to consider, is the food going to be worth it? In which case, you may have a different outcome. Ensuring that these teams are working collaboratively with you and have an awareness of all the important decision making factors and criteria is really important on what makes a good model. Models aren't good or bad, they are just reflective of the inputs and decision making criteria that you give them. So we'll take that decision. But if you are anything like me, you may sweat the decision a lot and weigh quite a few different factors on whether or not you want to attend your colleague's party and make a more complex decision. So each layer makes decisions based on the decisions made in the prior layer. These are called deep neural networks. It's an artificial neural network with multiple layers between the input and output layers. Often, there can be dozens or hundreds, even thousands of different layers between the input and decision output. So let's shift gears a little bit and take an image recognition task here. One of the things that you want to use for neural net is to do character recognition. In this case, recognize the input of a handwritten 7, which in an image represents actual multiple pixels in a grayscale, and each pixel has a value between 0 and 255. And you need to understand the order and where those pixels are in an image. So it actually has 784 different inputs here. If this 7 is drawn on a 28 by 28 scale, as you can see, 784 inputs, and the inputs are each of the individual pixel values. A deep neural network takes the input from each of these pixels and makes a series of subsequent decisions, so that output of this neural network can recognize the number. It's a 7, one output neuron for each digit. The neuron with the highest value is the predicted digit. It could perhaps also have an output that's a 1, because they may look similarly depending on how it's drawn. But what it's going to give you is the confidence that it's most likely to be. These neural networks are trained by large amounts of paired input and output values. In this case, a lot of examples of handwritten numbers are categorized into which digit they are representing. You probably use this every day in reality, which is mail system, which uses character recognition to route mail incredibly efficiently. So neural networks are some of the most common models used in ML. A single neural network is made up of numerous computational layers. Each of these layers will pass a decision to the subsequent layer until reaching the output layer, which will produce a final decision for the input data. The data that goes into the network is a set of values. These values, for example, could be pixels contained in an image or audio waveform. The image shows an example of network with 3 layers, 2 hidden layers and an output layer. When counting the number of layers, we generally count all the layers after the input layer. Each layer is made up of some number of nodes, each of which has its own parameters that describe the flow through the network. Neural networks are sometimes referred to as deep neural networks, simply because of the deep number of layers contained in the network. Before a network is trained, there is an architecture that is defined and used throughout the life of the model. There is a process known as neural architecture search that further optimizes the creation of neural network by swapping out and testing different architectures as the model is trained. We'll go into this a bit later, but to start, we should understand that a neural network is a series of layers, each of which contains different nodes which will perform various calculations. The structure of these nodes and layers, as well as how they are connected, is what is known as the architecture of the network. So now let's go back to our previous example of determining whether or not we should go to a co-worker's party. This is a network with a single node. We had 3 inputs along with a weight for each input to show which ones were most important. Indeed, we found that adding these weights is critical because they allow us to adjust the likelihood of a certain decision based on inputs. In this example, it meant that we absolutely cannot attend the party if we are not free, which is sensible. The other factor that allowed us to come to this conclusion was the decision threshold. Had we set a decision threshold of 3 instead of 7, then indeed there would be a case when we would choose to attend the party even if we aren't free. Now, it is clear in this example that we want a threshold above 4 to handle the case that we aren't free. However, you can imagine if we are looking at pixels in an image or large document of text that this decision threshold may not be so easy to determine. This is where we see the application of activation functions. Now, activation functions are functions that we can use as decision boundaries to tell us whether or not to send a signal to subsequent layers in the network. Furthermore, activation functions allow us to pass a range of values to the following layer instead of a strict 0 or 1 for a yes or no. As I mentioned, activation functions serve as individual nodes' decision boundary that will determine the signal that is passed on to the subsequent layer. An ideal activation function would return a range of values which will allow us to scale the node's output rather than having a binary yes or no decision. Starting with these activation functions, we will piece together the different parameters that are tuned when training a neural network. To illustrate this binary decision boundary, a basic threshold is in essence a step function. This means that until we pass our threshold, we do not pass a signal. That is, we have a 0 or no decision, and once we have reached the threshold, we immediately jump to 1. That is an absolute yes. Now, in this case of attending a party, a yes or no decision is fairly obvious. However, when executing a complex task such as transcribing a document, we want to allow for some uncertainty so that even if the machine's transcription is not perfect, we can still get a decent output, after which we can have a human make minor adjustments if necessary. Just like shipping products, allowing machines to make decisions means we have to allow them to be imperfect. This means that we need a better decision boundary that will give us room for error. One such function is called the sigmoid function. Using a sigmoid function, we receive an output with a range of 0 to 1, and this provides continuous decision boundary where each node in the network acts as sort of a knob. As the network is trained, these knobs are adjusted to produce the optimal output. So the way to think about this is that when training the network, we will have to adjust the parameters on each node in the network. Two of the other common functions are the ReLU function and the leaky ReLU function. These simplify the activation function to a linear equation which allows for faster and less complex training. The general idea is that we don't pay as much attention to the negative inputs, which reduces the number of nodes that are activated, thereby simplifying the network. These are the most commonly used activation functions to generally perform the best amongst the activation functions. So going back to our example, we now want to update our model with one of these dynamic activation functions to allow the model to provide more insightful decisions. We start by substituting the decision threshold with one of these activation functions. Here we'll go with the sigmoid since we want a go or no go decision. Now we can use placeholders for the weights which will be set when the model is trained. Now we have a node that is completely configurable. Instead of having hard set weights and a single threshold, the training process will now set these weights based on the labeled data. Given an input, you will provide the machine with the desired output via your training labels in the training data. The machine will incrementally update those weight parameters to best optimize the model for all input-output pairs. This is how the model learns from the training data and why the training data is absolutely critical to the model creation process. The actual method for updating the weights is called backpropagation. So you don't need to go into the details of it, but just so that you know, it is an algorithm used to automatically update those weights on the inputs in each node. Now one more thing I want you to know is that the node shown here is of a specific type of node called the perceptron. In machine learning, we actually have different types of nodes that each of which has their own pros and cons and are used for various applications. To give you an idea, the node that we saw previously is called multi-layer perceptron, which is a specific type of a neural network. The idea is that you have bunch of these perceptrons connected in layers without outputs of a previous layer feeding inputs to a subsequent layer. Another type of network is called convolutional neural network, which is widely used in computer vision tasks such as image classification and object detection. On the bottom, you see a LSTM or long short term memory network, which is commonly used in natural language tasks such as speech recognition. Again, you don't need to go into the specifics of each of these networks, but know that there are different types of nodes and networks that are specialized for various use cases. So let's see a quiz. Now, which of the following are true about activation functions? Check all that are true. Thresholds are the best activation functions because they are easy to set and simple to change. The next is sigmoids are useful activation functions because they return a continuous range of values between 0 and 1, allowing range of decisions rather than just yes or no. The third one is ReLU functions are useful activation functions because they are linear from -infinity to infinity, which simplifies the decision boundary. And the last option is ReLU functions are useful activation functions because they are non-linear but with two distinct linear slopes below and above 0, which give less significance to negative node outputs. So in this quiz, we wanted to identify which of these statements are true about activation functions. Going through the list, we see the option A discusses about thresholds. We saw that using thresholds are not the best options because they act as step functions which simply returns a 0 or 1 instead of a continuous value. Looking at the next option, we do actually like sigmoids because they return a continuous range value between 0 and 1, allowing a range of decisions rather than just a simple yes or no. Looking at the third and fourth point, we see that they both are discussing about ReLU functions. However, in option C, it says that they are linear from -infinity to infinity, which is incorrect. ReLU functions in fact have different slopes below 0 and above 0. This is why we select B and D as the correct options. So we looked at a high level overview of modeling and machine learning. We learned that neural networks are the basis for much of the ML we see today. These networks consist of nodes that are linked together through inputs and outputs with activation functions that determine whether or not a node will forward information. The most common activation functions are the sigmoid and ReLU functions because they produce a continuous output allowing for a range of values passed from one node to another. Weights on the inputs of each node are tuned and ultimately define the behavior of data flowing through the network by throttling each input's impact on the node. Additionally, there are different types of nodes and networks that are specialized for specific use cases. So now let's talk about training data. So training data is like the currency of machine learning and is the basis of learning component in ML. A good way to think about neural networks in the context of training data is to imagine a young child that has never seen a car. After being told what a car is and interacting with different types of vehicles such as buses and trucks, the child will eventually learn what a car is and can identify them in the future. Similarly, a machine learns by looking at many examples of a given object, and it will eventually learn that pattern and data can be associated with a specific classification. Now, unlike children, machines are much more difficult to train and require special care and attention to ensure that they are learning the correct concepts. In machine learning, the data is the key to model performance and outcomes. If you want a model to learn a specific concept, it must be clearly represented in the data in order for the machine to learn it for the future. This means that, for example, if you want a machine to learn to detect animal sounds and audio, you must provide the machine with examples of all the types of animals you would like it to learn. Furthermore, if the data you use to train the models is inaccurate, for example, you have humans making these animal noise, then it's unlikely to work on real animal sounds, as it has only heard simulated human sounds. With that said, let's go through an example of training a model to see how the model behaves when it's given different types of training data. Here, we want to train a model that can determine the type of pet in an image. To start, we have batches of labeled data that are fed into the network for training. Once a network is trained, it retains all the knowledge learned from the example images. In this case, there are two classes of animals that are represented in the model, cat and dog. Now, when the model sees a new image that is not previously seen, it is able to predict the animal contained in the image. As we can see, this works great with images of dogs. Similarly, if we feed in this image here of a cat, the model is able to determine that this is a cat. In these examples, we can see that if the model is given unknown data, as long as the data is similar to the training data, then it is able to infer the content of that data. In this case, cats and dogs. Now, if we feed this image into the data, this proves problematic because the pet contained in this model is not one that is represented in the training data. Therefore, a cute gerbil was assigned the label of a cat since the model has only knowledge of cats and dogs. In order to remedy this situation, we can train the model on a third class of gerbil images. Now, the model is aware of the gerbil class of pets. When we feed this image into the model, we now indeed get the correct predicted label of gerbil. Now, we can see that if the model is not given a particular type of data, it will never be able to infer on the other types of that data. Only after being trained on a given type or class of data will the model be able to begin to make predictions of that type. So some of the key points to note when training a model is that you must train it with all types of data that the model is likely to encounter in the future in order to build a robust model. Adding diversity to your data is also very important because similar to how the model did not know about a gerbil class until it was shown the correct data, if the model encounters only dogs in the snow, then it is very unlikely to identify a dog pictured in the field of grass. Like I said earlier, models require proper care and attention to be robust in performance. To illustrate this in another example, let's imagine that you want to build a model to recognize shoes. Like in the previous example, we start with some training data. In this case, 3 different images of shoes. In order to get a diverse set of data, we've also included a sketch of shoes. Now, once we have trained the model, we put the model into the wild and try to run some of the real world data. As you probably guessed, this is not going to work. The training data represents only a very specific types of shoes, clogs. While these may prove to be great footwear from Northern Europe, they do not represent all types of shoes that we see today. Instead, let's train our model on a more diverse set of footwear. Here, we have included boots, sneakers, dress shoes, and even flip-flops. Now, when we see a real-world example, the model will be able to correctly identify the shoes. So, looking back at these examples, we should understand that the data used to train the machine learning model is absolute the key to producing a robust and usable model in the real world. Depending on the intended usage of the model, we want to make sure that we are using diverse enough data, which means understanding all the potential scenarios that the model is likely to encounter and accommodate for those in the training data. Additionally, we want to reduce the amount of noisy data as much as possible and ensure that these labels that we are providing to the machine are accurate. Next, I want to walk you through some of the common issues we see in training data that can significantly impact the outcomes of our model. First off is the distribution of training data. In this chart, you can see an example of an unbalanced training data. Of the 4 classes, 2 of them, cat and dogs, have significantly more training data than bird or snake. This may be due to a number of different factors, including the fact that snakes are less common pets than cats or dogs. In cases of unbalanced data, the model will learn significantly more about cats and dogs rather than the other classes and will tend to bias towards those classes when running in the wild. In order to prevent this outcome, we want to collect more training data for the classes that are lacking or reduce the amount of training data for those that have too much. While more training data will often lead to a better model, balancing the data is as important, if not more, to produce an unbiased model. The second case is similar to the example with shoes we saw earlier. This is where the training examples are different than the real world examples, even when they technically fall into the same class. To put this in an example, here you can see 2 audio recordings. The recording on the top was collected in a recording studio, while the one on the bottom collected from a mobile device. As you may see, the audio collected from the mobile device has a great deal of noise, as the case is in real life situations. If we were to train the model only on studio audio, our model would fail miserably at detecting audio collected from mobile devices. This is an example where we want to be aware of what the real world data may look like so that we can collect the appropriate data. Next, we have the issue of mislabeled data. While you may think that it is very difficult to mix up a dog and a horse when labeling images, you can imagine in this example where we are parsing entities out of text. In this case, it may be quite difficult to properly label the data, as it can be unclear where particular entities should be classified. In this case, we want to be very careful when assigning labels to our training data and ensure that when we are collecting the data either manually or through a large platform provider, the labels that are returned are accurately classified as expected. Finally, we have the quantity of training data used to train our models. This is actually much more fuzzy, as the amount of data required will vary widely based on the number of factors, including the data type, complexity of the data. Again, you want to make sure that you are thinking about what the real world data looks like and the model architecture itself. While there is no clear-cut rule as to how much data will be needed, we generally want to start a few hundred examples of each target class and then scale up the amount of training data until we reach a desired accuracy. So let's see a quiz. So, what data would you need to train a voice assistant for a hotel concierge service? 2 hours of audio data of people talking to a hotel concierge. 10,000 images of a hotel concierge activities that may include check-in, check-out, bellhop, doorman. 10 hours of audio data of concierge desk conversations and 50 hours of audio data of the most common guest concierge interactions with data collected from a studio, from a hotel room and with sufficient ambient noise. 50 hours of lobby video and audio with ambient audio and video data to ensure robustness in different situations. And the last option is you can't train a model as a voice assistant. So in this quiz, I wanted you to identify what type of training data is best used for creating a voice assistant for a hotel concierge service. When we look at the options, we can immediately start to eliminate a few of them. So if we look at option B, we see that it's calling for 10,000 images of hotel concierge activity. We can immediately remove this because in order to train a voice assistant, image data is unlikely to be of any use. Similarly, we can eliminate option D because that is calling for video data, which is essentially a series of images connected together. Then we have options A and C left. Option A, while it is collecting the correct type of data, we see that it is only collecting 2 hours of audio data, which is unlikely to capture all types of scenarios that you may encounter in a hotel concierge. This leaves us with option C, 10 hours of audio data of concierge desk conversation and 50 hours of audio data from the most common guest concierge interactions. As you can see, this will capture a fair amount of real world data as well as diverse data from different locations, which will provide us with a sufficient dataset to train our voice assistant. So there we are. In machine learning, the training data is key to building robust AI. We rely on the data to give the machine all the insights needed to process the real world data. If we remain aware of the types of data the model will encounter in the wild, then we can tailor our training data to encompass as many cases as possible. While it may not be feasible to cover every corner case, over time we can monitor the performance of the model and understand where the model performance is weak and update the model as necessary. So in the next few minutes, we'll go over exactly how to evaluate your models to understand where the model is performing well and where the model is lacking. This will allow us to ensure that the models we build will be successful when put into production. So let's discuss about the specific methods to measure model performance. Having clear performance metrics will allow us to understand where the model is performing well and where we need to pay more attention. We will be stepping through examples to make it as clear as possible. When measuring model performance, we want to have sensible metrics that indicate how well the model is performing. This should encompass the model's ability to predict each of the trained classes and give us an insight into any biases that may exist on the model. By having these clear metrics, we can get a good idea of how the model will perform when deployed into production, which will ultimately guide the performance of the product and its impact in the market. So in order to measure a model's performance, we use data similar to how we use data to train the model. From the total set of labeled data, we generally use 80% for training data and the other 20% for testing the model. It is important to note that training data and test data should both be as balanced as possible. Similar to the issues we saw in training the model, having unbalanced data in the test data may skew our perspective of the model's performance. For example, if the test set is made up of a majority of a single class, then we will not have robust enough test cases to determine whether the model is performing adequately across all classes or not. In addition to test data, validation data is sometimes added as another split. The validation data is used during training to help inform updates to model parameters and is different from the test data because the test data is never seen by the model until the training is complete to simulate a new set of data that the model has never seen. This way, we can evaluate how the model would perform on data that is completely different than the data we used in training. The way we evaluate these models is to start with our labeled test data. We feed this data through the network, which produces each of the labeled data points. By comparing the predicted labels and the actual labels, we start to get an idea of where the model is performing well and where the model needs improvement. We need a measure of performance, so we could count the number of correct and incorrect predictions. However, we want to understand the performance of each class, which requires more than a simple count of incorrect versus correct. Two common measures we use when evaluating a model are precision and recall. Both of these will measure the model such that we can understand how the model performs for an individual class as well as how well it performs across classes. Looking at this graphic, we see that the model's predictions inside the circle. The left half of the graphic represents the ground truth in the data, and the right half of the graphic represents negative or non-existent data. To give an example, if we had three images of cats and only two of them were correctly identified as cats, we would see the two correctly predicted cats on the left half of the inner circle and the missing cats on the left half of the outer square, representing a false negative prediction. Conversely, if we misclassified a dog as a cat, that would fall on the right half of the inner circle as a false positive. A model's precision answers the question of when the model makes a prediction, how likely is that prediction to be correct. In order to calculate the precision, we will take the number of true positives, that is, the number of correct predictions, and divide it by the total number of predictions. And that will give us what percent of all the predictions were correct. We start with the predicted labels for each of the data classes. We will first calculate the precision for each class. For cats, we take the number of correctly predicted cats and divide that by total number of cat predictions. In this case, we have only one correctly predicted cat and two cat predictions. One for the actual cat and one for the misclassified gerbil. So this gives us a precision of 0.5. Similarly, we do the same calculation for dog and gerbil classes. In the cases of gerbils, where zero gerbil predictions were made, we simply assign 0 precision. There is another reason why we want enough test data so that we will have at least one prediction for each class. Now, to find the model's overall precision, we take the average of all the precisions. So we can say that we have a model precision of 0.5 or 50%. Next, we'll take a look at how to calculate the model recall. So model recall answers the question of how good a model is at identifying actual occurrences of objects in the data. This will give us an understanding of whether or not the model can recognize these objects. We calculate the recall by taking the number of correct predictions and divide that by number of actual occurrences. This will tell us what percentage of real occurrences were recalled by the model. Again, we start by the model's predictions for each data point. We go ahead and calculate the recall for each of the model classes. This time, for cats, we take the number of correctly predicted cats and divide that by total number of real cats. In this case, there is only one correctly predicted cat as well as one actual cat. So this gives us a recall of 1. We then do the same calculation for all other classes and take the average of all the recall values. In this case, our overall model recall is 66%. So as you can see, both the precision and recall of the gerbil class are very poor, which indicates that we may need to improve the model for this class. Additionally, while the recall for the cat class is 1, we saw that it has a poor precision of 0.5, which means that the model may be biased towards the class, causing erroneous cat predictions. A third measure that is commonly used is called the F1 score. The F1 score combines the precision and recall to produce an overall performance measure of the model. The F1 score ranges from 0 to 1, with 1 being perfect precision in recall. Generally, an F1 score above 0.75 or 0.8 will be considered decent. However, it will depend on the intended application and how critical the performance of the model is to the success of the product. In our case, we saw that an F1 score of 0.57, and it indicates that the model definitely needs more training cycles in order to improve the overall performance. Finally, we can plot a confusion matrix to understand where are our problem classes, and we can get an insight into how we should update our model. The confusion matrix is a grid that shows all the predicted labels relative to the true labels. When looking at the chart, the values across each row should add up to 100%, while the values in the column have no limitations. This chart shows that 100% of the true dogs were classified 100% of the times in the dog category. Similarly, 100% of the cats were classified 100% of the time in the cat category. The gerbils, on the other hand, reclassified 100% of the time in the cat category as well. This shows us that the cat category is getting an unbalanced number of predictions while the gerbil category is not getting enough. This should give us some insight into where we can improve our training data to increase the model's accuracy. Now recall why are training and test data separate? It's because we use training data when a model is learning. In our cat, dog, gerbil example, this is the data a model can use to learn and find patterns that distinguish the different classes of images. After training, we need a way to test how well a trained model generalizes. The idea is that we want to train a model to perform well on new inputs that it hasn't seen before. This is where the test data becomes very useful. Because a model hasn't seen it during training, we can test it on the dataset and evaluate its performance. So let's see a quiz. In this quiz, you have to calculate the F1 score given the following confusion matrix. So here, I want you to calculate the overall performance of this model given the confusion matrix and these ground truth labels. The intuition for this answer is we calculated the recall for each of the classes. We next calculated the precision for each of the classes as well, and we found the overall model recall and precision. Once we had these, we plugged them into our formula for the F1 score and got an overall model performance of 0.75. And this gives us a good indication that the model is performing really well but could still benefit from additional training. And that sums up our model evaluation. We use test data to calculate the precision and recall for each class on the model, as well as an overall model precision and recall. We use the metrics to calculate an F1 score, which gives us an overall performance measure for the model, taking into account correctly and incorrectly predicted examples for all classes. We also plotted the predictions on a confusion matrix to get into where the model biases may occur and which class we should focus on in the future training cycles. Next, we will talk about transfer learning and automated ML. These are two facets of machine learning that have made the development of ML models more accessible to developers, as well as to the individuals who may not have had as much engineering or scientific background. So now we move on to transfer learning. Transfer learning is when we use the knowledge from an already trained network with a similar use case which is stored in the architecture of the network as well as the weights and adapt that to a new use case, generally that requires different classes. This allows us to develop models with significantly less data because the neural network can retain the knowledge it learned from the previous training data, sometimes millions of data points, and slightly tuned parameters to fit our needs. Now, automated ML takes this one step further by allowing us to build relatively robust and scalable models without much machine learning experience. In order to do this, we take the first n layers of the pre-trained network. The number n is generally all except the last few layers depending on how deep the original network is. Then we copy these layers into a new model. These copied layers will retain the same architecture as well as the same weights and activation functions. Then we will attach new layers to the end to replace the old ones. Here you can see the number of output nodes is actually different between the two models. This is because in the first model we are supporting 4 classes. while in the new model we only require 2. Once we have the new network, we go ahead and retrain it to tune the last layers of the network that will give us the supported classes that we are looking for. In this example, we copy the weights from the first n layers into the second model and only retrain the last layer of the new model. This is specifically called transfer learning, where the weights on the earlier layers do not change. Another version of this is called fine-tuning, where you use the same process but also retain the earlier layers. Each model has its pros and cons and will be largely dependent on the training data that is available. But at a high level, the idea behind transfer learning and fine-tuning is that we can leverage the knowledge that was previously learned and make slight modifications to accomplish a different task. This will generally reduce the amount of trained data necessary to accomplish a particular accuracy, which makes creating models using transfer learning and fine-tuning much quicker and cheaper. Today, we see a lot of these pre-trained models available for free online. By using these pre-trained models, some of which have been trained on millions of data points, we take advantage of previous training cycles and require much less data to adjust or tune the model to identify our desired classes. So why does transfer learning work? In the example above, we are leveraging the weights of an existing classification network, one that classifies cats, dogs, rabbits, and horses. We are keeping the first few layers of the trained network, then adding and retraining a final classification layer to create a new classification network that identifies humans and birds. But why are these first few layers helpful? Well, in the case of image classification, the first layers in a network are responsible for identifying general patterns in shape and color, such as simple lines and textures that distinguish different classes of images. Later layers identify more complex features such as eyes, ears, and feet. The earlier layers, because they identify simple patterns, will be relevant in any classification case. There will always be simple lines and colors that we can use to identify different objects. And that is why you can transfer learnings from earlier layers of one network to another. Now coming to automated machine learning, this is where cloud service providers such as Google Cloud and IBM Watson offer ML model creation services. The way these services work are that you bring your labeled data to the platform and they will automatically train and tune your model to fit your case. This allows you to easily build and test an ML model with little additional work to actually serve the model. One major benefit along with this platform will come enterprise support. This combination offers an overall solution with significantly less complexity. An added benefit of using these services is that many of them will conduct neural architecture search on the back end. This will automatically select the optimal architecture for your model by fitting various components together and assessing their accuracy. All of this will be handled by the service provider and is often how they are able to effectively scale their ML solutions. So when thinking about building ML interdependent products, we can now look at different options of build versus buy. With automated ML, you will get easy setup and robust enterprise support. But this will come at a cost of limited use cases and possibly sharing sensitive data with a third-party provider. On the flip side, with building a custom model, the possibilities of customization are left to the imagination. But the drawback is that it can be costly to build and manage. So that's the end of this section. We saw how transfer learning can be used to leverage knowledge from other models to speed up the creation of new ones by copying a portion of the first model and tuning it for a specific need. People often post pre-trained models online, which had been trained on thousands or millions of data points and often serve as a great starting point for model development. Automated ML is another segment of machine learning where service providers will offer tools to create ML models. Generally, these platforms will have a limited set of use cases. If there is a need for more complex models, then a custom model may be the way to go. So now let's move on and talk about the AutoML in general and get a feel for it. So let's have a discussion about automated ML. So what is AutoML? Well, AutoML stands for Automated Machine Learning, as we have seen earlier also, and it is the effort to fully automate end-to-end the machine learning process. Now what this means in practice is that we try to build systems where you just throw your data in, you click a button and get results. As we say, you declare what you want and the system knows how to compute it. Now that of course sounds extremely ambitious. So the term AutoML should be taken with a grain of salt. We gradually try to automate bigger and bigger portions of machine learning, but as of now, there are absolutely no systems that can fully automate all types of machine learning, from predictive modeling with, let's say, sequences to learning with graphs to casual discovery. Now let's take an example of a system called JADBio. It's a system that fully automates predictive modeling with tabular data, but not unsupervised learning. Now some people confuse AutoML with what is technically called as cache. Now cache stands for Combined Algorithm Selection and Hyperparameter Optimization. So cache are algorithms for optimizing the combination of algorithms to use at each step of the analysis, like transformations, imputation of missing values, feature selection, modeling, etc. And there are hyperparameters, but in the end they just return a predictive model. The most famous example of a cache library is the very successful, admittedly, Auto Scikit-learn system, but it only returns a predictive model. However, AutoML should be much more. It should not just return a model. This is not only what a user needs. AutoML should return estimates of what predictive performance to expect from the model, and it should perform feature selection, help interpreting and explaining the final model, and help the user to make decisions, put the model into operational environment, monitor its execution, raise alarm predictions starting to go off, and much more. It should provide everything a good machine learning engineer would provide to you. So that's what AutoML means. So I guess the question now is, if AutoML does everything, who is it for? Is it for academics or industry people, or is it for people that are already experts, or is it just for beginners who are trying to learn machine learning, or who is it for? So if you think about it, the beauty of AutoML is that it should be for anyone, and I mean anyone, and not just ML or AI engineers. From CEOs who analyze their company's data to a home dad who wants to analyze their expenses Excel sheet should be able to use AutoML, not requiring any coding, math, statistics, or machine learning. AutoML should be democratic and should bring machine learning to the masses. We should build optimal systems that follow the path of Microsoft Excel. And here's what I mean. Initially, MS Excel seemed to only appeal to people who were accountants. And now everybody uses it, from a teacher who's keeping track of student grades to a higher level executive. Now, it may seem at first that AutoML is meant for novices and non-experts, but this is absolutely not true. It really boosts the product activity of expert analysts too. And in fact, some of the people who best appreciate AutoML are experts who are fully aware of the difficulties and challenges of doing it yourself and can feel the pain and effort that AutoML takes away. Programmers used to program in assembly language decades ago, and now they are programming in Python, which is much more automatic. Programmers benefited from making programming languages higher level. So I think it's the same with AutoML. Instead of scripting all the details of an analysis, experts can now automate many parts of it, and can focus on other aspects of the analysis like data representation and interpretation of results. So now this begs the question, how does AutoML compare to manually optimizing a bunch of models, and is it better to do it by hand or is it better to use AutoML? So it's difficult to prove or disprove the statement scientifically because it will depend on which human experts do you actually compare against. So it would take really big studies with lots of experts with different levels of expertise to get sound results. But without scientific evidence, let me tell you a story. So, Jad Bio recently participated in an FDA prediction challenge to predict the survival time of brain cancer patients. So, what they did was they downloaded the data, uploaded it to their signature platform, Jad Bio AutoML platform, clicked and got results within a few minutes of manual effort. And they came in at third place out of 30 participating groups. Now, the winner submitted a model that had only one point of C index higher than theirs on the holdout set. Now, what the C index is, it's similar to the area under the curve metric for measuring performance. So, the difference was really not that big, and it was within the confidence intervals, within the uncertainty of the estimation. So, it may just have been luck for all we know that they couldn't finish first. Now, we don't know how long the winning team spent on the challenge, but it was hundreds of hours compared to the minutes of manual effort that Jad Bio engineers put in. Now, having said that, many analysis problems do require an expert to pre-process data, clean the data, represent them in a suitable format, formulate a problem as a machine learning task, and make it ready for AutoML. So that's where the human is still unbeatable. But once the data is ready, be aware of AutoML. So now the obvious question that comes to mind after listening to the above scenario is that will AutoML replace data science jobs, or it will just make those jobs more interesting? Now if you think about this, has something like this ever happened before? I mean, never, right? You go from assembly language to using Python, and instead of firing programmers, now the global economy needs more and more programmers. So right now, only about 5% of the global data is actually ever analyzed. And what I think is going to happen is that the demand for analysis will increase with AutoML because people, businesses, scientists will be able to unlock the value of the data that they are sitting on, and they will be hungry for more. So AutoML will definitely boost the productivity, but at least for the foreseeable future, it will not eliminate the need for an expert. You will still need the expert to represent and formulate the problem as a machine learning task, interpret the results, and apply the model correctly and for this type of stuff. So the difference, however, is that the experts will have to be more specialized, more educated, and more sophisticated than before. Right now, people perform a cross validation of a random forest in Python, and they feel that they are entitled to write data scientist in their resume. So these simple tasks, I think, will be automated and will be performed with much higher quality, that is, with no errors and no overfitting by AutoML. So the next generation of data scientists will have to add more value than that to the whole process to justify their salaries. So now let's discuss about the future of AutoML. Well, it's a very bright one. I think that the era of manual scripting for machine learning is reaching a critical point. It is changing, it is evolving. It could be that within 5 years at most, data analysis will be completely performed by all the ML systems, or at the very least, there will be an automated system like an AutoML system doing a major part of the analysis. Now, experts may be still scripting, but the scripts will be calling AutoML systems and configuring AutoML systems and customizing them instead of being from scratch. So, it will be scripting on a higher level, and I think there are great opportunities business wise for startups and investments in this space. It could be possible lots of different types of companies will need to have an AutoML internally embedded in their products in order to survive. For example, database vendors, data ranking companies, cloud providers, and so forth will need to own an AutoML system to convert automatically the data stored by their users to actionable knowledge. You may well see AutoML systems embedded within other softwares too, and we may not even know it. For example, we will have like AutoML within laptops, cars, and other devices to keep analyzing the data from our behavior and our usage of these devices and our interaction with the environment of these systems to make them even more smarter. So that's what I think about the future of AutoML, and well, it sounds very bright. So now moving ahead, in this section of the lecture, we are going to take a look at some relatively new services on the Google Cloud or on machine learning. These are in the category of what I call SaaS services or software as a service, specifically machine learning services. And they are marketed as APIs, application programming interfaces or endpoints. Basically, the way that they work is you look at the type of data you want to analyze. So, is it photos, videos, text, speech, so on and so forth. And then, based on the type of data, you send it to a particular machine learning endpoint. The Google Cloud Platform machine learning endpoint will return to you many types of labels and optionally likelihoods of that particular label. So again, to make this concrete, there is a Vision API that allows for analysis and classification of photos. So if we had our cat and dog example, we could simply upload our photos and we would then be able to see labels related to what the machine learning API thought was in those photos. Now for some business scenarios, this can provide all the necessary usefulness to meet the customer need. So what's great about this is basically you're just paying for an invocation and you don't have to select an algorithm and you don't have to select a machine learning model type, set the hyperparameters, train it, tune it, deploy it, so on and so forth. It's really, if you think of it as a serverless machine learning. Now, of course, you have to authenticate and you are going to pay for the invocation. So if we look in our hierarchy of machine learning services, the machine learning APIs sit at the SaaS level. If you are going to be using photos or videos, then you would use the Vision or Video Intelligence APIs. If you are going to work with the language, and that can be either text or speech, you have a number of APIs to work with, like natural language, translate, speech to text, text to speech, and something called as talent, which relates to jobs. So both for people seeking jobs and for people advertising jobs. Now very new in the ecosystem is a conversational API called Dialogflow, and then I categorize an extension to working with a big data service which is called BigQuery Machine Learning as a SaaS type application, and I'll show you why as we progress through this section. The first API in the set that we are going to look at is the Vision API, and this is designed to work with photographs. So it's going to produce many types of labels and optionally a probability of that label which is expressed as the word likelihood or confidence, and that's a number always. So here you can see I have pulled up the API Explorer and you can see that there is a rich set of fields or labels that can be included in the response. So you can have crop hints around if you want to crop the photo, face annotations, so faces can be discovered, full text annotations, image properties, labels, landmarks, logos, safe search, text annotations, and web detection. For your particular business scenario, you're gonna want to explore this API and figure out which of these annotation types are going to provide the value for your application. Here's an example of calling this API using a Python script and returning the face annotation attribute. So you can see on the left side we have a photo and on the right side we have a bounding box around what the API finds to be a face in the picture. And if we just go through the Python code here, we've got a main method and we have input and output files and max results. So we could call this and just pass in those values. And then we would open the input file and then we would detect a face So that would be the image max results. And then we would print that we found a face. And we would simply call the highlight faces method on the image and pass in faces in the output file. So now let's explore the Google Cloud platform, and what we want to do is create a free account on Google Cloud. So first let's navigate to cloud.google.com, and then at the top right we have this option to get started for free, and we click that. Now this will ask you to sign into the Google Cloud platform. Now for this demo I am creating a new Google account for demonstration purposes. So I will create a new account and then I am going to fill in my details, and so once this is done we click next, and then we have some other details also to fill out. Then just go ahead and agree to the privacy terms. So as you can see that here we get a $300 credit for free to use in the next 90 days. So just go through everything carefully and then agree to the terms of service. So to move on, we click continue and we fill in some more details here, and you will have to add a credit or debit card in here. But don't worry, you won't get charged. So now of course you want to be very careful and aware that as soon as you're done using this platform, you should remove your card details, and you should also be constantly monitoring your billing to see if there are any charges that have been added. So these details are important to put in, and you won't be able to proceed unless you have provided these details. But don't worry, $300 credit is a lot and it won't get over. So now once this is done, the billing will be set up and we get this welcome message here, and that says our free trial includes $300 in credit. So once you click got it, we click go to checklist and we complete some common tasks so that our account is set up properly. So just follow the steps in the checklist, and once your billing account is created, you can create a project and then we will be good to go. And then we can also explore the APIs. So this is quite an intuitive process and everything is quite self-explanatory. So I encourage you all to just play with the tool. So you can see here that there are different APIs for the platform, and we can see the image classification under AutoML Vision API. So let's get started. So to get started, to build an AutoML Vision classification or object detection model, we need to first enable the AutoML API. So let's do that. Now once you will try to do this, you will get an error message here saying that the API failed to get enabled because of some billing issue. Now although we have entered our credit card details, it doesn't mean that the billing has been enabled for the API. So what we do is we go to our Google Cloud dashboard, and so here on the left you can see all the project information for the project that I have created. You will be able to see it in the same way. So you can click on the navigation bar, and that's provided on the top left, and we go to our Vision API, and then we'll try to enable the AutoML API again. Now again it shows that the API has been failed to be enabled and we get that error message. So to resolve this, we use the navigation on top left and we go to the billing section. So what we basically need to do here is that we need to link our billing account for our project. So we click on this option, link a billing account, and then we select that account and we set that account. Now once this is done, you can see the billing account overview and you can see the free trial credit over here at the right hand side. So now our account has been set up and our billing details are linked. So in this section of the lecture, now we are going to take a look at some of the relatively new services on the Google Cloud or on machine learning. So the first API that we are going to explore is the Vision API, and this is designed to work with photographs. So it's going to produce many types of labels and optionally a probability of that label which is expressed as the word likelihood or confidence, and that will always be a number. So we go to cloud.google.com and we go to products and we click on AI and ML just below the feature products on the left side, and we see the Vision AI API, and we click on that. So this brings us to the Vision AI page, and now if you scroll down a bit, you will see the try the API option. So if we click on the box to upload an image, you will be able to upload images that I have provided you. You may also choose any image that you like and feel free to explore the API. So to explore this API, I have chosen a pink sky image and I am going to upload that. So once that's done and I have uploaded the photo, and in real time, here are the results that you can get back from this photo from the Vision API. So you can see here that there are a number of categories across the top, and we are in labels category here. And you can see here that we've got the labels and likelihood. So we can see 97% sky, 98% clouds, so on and so forth. And they are in sorted order. So if you click on the objects, you can see that it has detected a street light in the image, and there is a green colored bounding box that has been drawn around it. Now we have already seen the labels, but we can just scroll down and see all the likelihoods. So we have here dusk is about 85%, sunlight is 84%, etc. So now let's move on to the text. Now what's interesting here is that we have OCR or text recognition. So it's really very hard to see, but actually there is a traffic sign on the street light, and you can see that the text in the traffic sign was partially red. And again you can see a green bounding box around the text in the traffic sign on the street light. So it seems like it recognized the text as speed limit of 25 when children are present. Now next we can move on to the properties tab, and here we can see the dominant colors and the crop hints. Then we also have safe search, and this is divided into various categories and our image is scored on these categories. So it can be seen that it says that it's very unlikely that our image has adult content, or it's a spoof, or it has violence in it, and so on and so forth. Then we also have the JSON field, and if we click on it, we can see the request and response. So this is just a great way to get started learning about the information that's returned by default in the Vision API. Now, as I've told you that there are a lot many APIs like the Video Intelligence API, Cloud Natural Language API, Text to Speech API, Cloud Translation API, and many more. But currently, Google does not allow us to try them for free like we did with the Vision API for images. So we will skip those for now. But you can feel free to explore them and get more information about them from cloud.google.com, and then by going to AI and ML products. Generally, the APIs are going to be the cheapest if they work best for you, because of course you have very little developer time here. You are accessing the endpoints rather than creating the models. So the cost savings in terms of development are substantial because you are working with trained models. So again, what I like to do from an architectural standpoint when I'm considering whether these APIs will work for my particular client is to do a total cost of ownership in terms of custom models versus using these pre-created APIs. Obviously, the output has to match what your particular need is, but in API that is so universal such as translation, this is often a good fit. So let's take a quick look at the GCP machine learning APIs, and I'd like to categorize them by the type of data. So if you have photos, you have the Vision API. There's a new service which we are going to cover in the next section called AutoML, which is important to consider for Vision. For videos, you have the capability to look at Video Intelligence API or Speech to Text API, which is used in data. As with the Vision API, the Video Intelligence API is available in AutoML and data as well, and we'll look at that subsequently. If your input type of data is text, then you have a number of APIs, and there will be probably more released in the future. So you have natural language which detects sentiments and entities. We have the jobs API which we did not look at, and this is sometimes also called as the career API. It's for both job seekers and job advertisers. The next is text to speech API, and we also have the translation API. As with vision and video, we have AutoML version, and we'll have a look at this pretty soon. For speech, we have the speech API, and we also have the dialog flow, which is a conversational API. Now, to round out our exploration of the GCP machine learning APIs, we are going to look at an extension to Google's BigQuery data warehousing and SQL on text file service, and this is called BigQuery machine learning. So this is just an extension to BigQuery for machine learning, and there are two types of machine learning models that we can create using the SQL-like syntax. Now the first one is linear regression, and an example of this model can be used for predicting a numerical value. So how many of something is it likely that will sell in the future based on our past sales history. And then secondly, we have the binary logistic regression. Now these models can be used for predicting one or two classes or categories, such as identifying whether an email is spam or not. Now we can use the SQL extension inside of the BigQuery console and set up this machine learning model. But I thought that it might be fun to work with our Jupyter notebook. So in this demo, we are going to work with the notebook and with the BigQuery language. So here we are in the Google Cloud Platform dashboard. Now what you want to do is open a new tab and type in colab.research.google.com. So this will open up this interface, and now you can just upload the BigQuery ML notebook file that I have provided you to the Colab interface. So we see that the notebook has opened up, and this is how the Google Colab interface looks like. Now in the first cell, we see that it's asking for the project ID, and it's going to ask us at each and every step. So you can just copy paste this information from your Google Cloud dashboard, and you will find this information under the project information category. So once you have copy pasted it, now we can run this cell, and it's very important to declare the cloud project ID that will be used for this notebook. Now once we try to run the next cell, we see that it asks for verification code. So we just need to click on this link, and it says to select our account, and we allow the Google Cloud to access our account, and that gives us a code. We just want to copy paste that code in our notebook, and then we press enter. So now here I have some irrelevant cells in my notebook, but your notebooks won't have them. So you don't need to worry about the irrelevant code, and I'm going to delete these cells here. So we come to using BigQuery machine learning. The next step here is to create a dataset in BigQuery. To do that, now in a new tab, we want to go to the BigQuery ML console. So the link to the console is console.cloud.google.com/BigQuery. And we see that we get a welcome message. Now to create a dataset, we first click on our project, and then once our project is selected, on the right we see there is a create dataset option. So we click that, and you want to use this name BQML tutorial, which stands for BigQuery Machine Learning Tutorial, and we click create a dataset, and there it is. And of course it's going to be empty right now. So now we can come back to our Colab notebook. So the first line is BigQuery %%, and using the syntax I've just put in my project number here, and then we are creating a model in line 2 that is of type logistic regression, and here we are using the big data public data from Google Analytics in the from clause of the query, and we are having a filter of just 1 year in the where clause, that is from 2016 to 2017. The logic in the select clause is to just address getting rid of nulls. So this can take a couple of minutes, but I'm going to go ahead and run this now. So now once it's executed, we can switch back to our BigQuery console on the Google Cloud. So let's go ahead and see what it looks like. Now if I go over to BigQuery and I open up the model, you can see that I have my model details here. So it says that model type is logistic regression and it's showing all the training options and the model details. Now if we go to the training tab and see the graphs, we see the loss curve duration it took for each iteration in seconds, and we also see the learning rate. Now if you don't like a graphical view, you can always opt for the table view, and it's the same information but presented in a tabular format. For each iteration here, we can see the training data loss, evaluation data loss, learn rate, and duration it took for each iteration. We can also check the schema, and it shows the labels and features and their data types and some more information. We can also go to the evaluation, and here we see different metrics on which we can evaluate our model. These are metrics that we have already seen before. We have the confusion matrix at the bottom, and we see some information here on the right like precision, recall, accuracy, and a F1 score. We also have the ROC curve and various other plots. So now let's come back to our notebook, and the next step is to look at the model statistics. And I did that in the user interface of BigQuery, but I can get the same information which we have seen, and we can get the information right from the notebook. So first, just let me copy paste my project ID here, and then I execute the cell. And basically you can see here that I get the same training information back. Now in the next cell, I am going to evaluate the model, and I am going to look at the quality of the models. So let's do that. Again, I have copy pasted my project ID and I execute this cell. And you can see here that the precision is 0.46, the recall is 0.11, the accuracy is pretty good, it's 0.98, and the area under the curve is also 0.98. So now we want to actually use our model to make predictions. We want to predict the count of purchases for each country, and then we also want to do this by the visitor ID. So you can see what's great about this is just you put a predict call in the middle of a SQL statement, and it's really innovative in terms for the ability for you to use core types of machine learning on data that you have already stored in BigQuery. And now don't forget to put in your project ID. So now when you are running this, what you are basically doing is you are selecting the country and then adding as predicted label the total predicted purchases from the model, and then you are dealing with the nulls again, and you are looking at the public information, grouping by country, ordering by predicted purchases, and putting the limit to 10 so it returns quickly. And you can see here in the output that US has got the most predicted purchases in this small subset of data. And then if we wanted to do the same thing, but now we want to do this by visitor ID, we would simply run the same query, and basically we can see this by visitor ID. So now you can see that this is really an interesting extension to the capabilities of BigQuery that so many of us use so frequently around in machine learning. So now let's take a look at the Google Cloud Platform Auto Machine Learning or AutoML. So what's AutoML? And we've seen this before. The idea is that AutoML will create a machine learning model using your labeled data. It uses Google Cloud Platform machine learning models, and so you don't need to select the model. Google provides it, and Google auto-tunes the model parameters. When you work with AutoML, you are going to be presented with model evaluation so that you can tune your input. Now, your input in this case is the data rather than model parameters. So in AutoML, you will be supplying labels and labeled data as input. And this does fall in the area of software as a service because you do not select the algorithm, the model, the parameters, or any of the other model building features that are associated with services that are platform as a service or infrastructure as a service or hosted on containers or VMs. You don't see that with this. Basically, you just supply the data. Now it's interesting because you see two different ways, for example, to work with Vision. So we'll be differentiating whether you'd want to use the Vision API, which is really a kind of serverless machine learning, and you just supply the data and you get the labels back, or AutoML for Vision, where you supply labeled data, you train a model that Google selects, look at the model results, and get your labels back. So, drilling into Vision, let's think about how AutoML works and why you want to use it. So in this example, rather than accepting the default labels that are output when you upload photos to the Vision API, you want to supply particular labels, in this case for photos. That's why you'd use the Vision AutoML API rather than using the natural language, for example. Now, in order to use this, you have to upload your sample data, photos with your labels. Then we are going to train the GCP model that Google's gonna select with our labeled photos, and then we are going to evaluate our model quality and iterate as needed. Now the way you can iterate is by providing more information about your data that is very specific to the type of AutoML that you are using. For us to visualize how AutoML works, if we look at this diagram, we are going to provide labeled data. In the case of Vision, so labels for our photos. And we are going to then use that data as a source to build an AutoML Vision model, and then we'll train it, deploy it, and the serve step that is transparent to us. So we can simply click train and Google will handle the deployment and serving, which also includes handling the scaling. So in effect, this is a kind of serverless ML in addition to the Vision API. As with the Vision API, to use your trained model, you will simply upload one or more photos and then labels will be output by calling the ML endpoint. So if you have photos plus custom labels, you will be using the Vision AutoML. In addition to manually labeling your photos, you have some other options to generate labels. We'll be looking at a mechanism using a zip file, which will automatically generate labels based on your folder hierarchy. And then we'll also talk about human labeling options that are available with the AutoML capability. Now, if you are working with text and custom labels, you have two choices. You can use AutoML for natural language or translation. And these AutoML capabilities work similarly, but of course they work with text. Now let's look at the AutoML using the Vision example in a bit more detail. So here we have some images that we'll be using with the AutoML to create our model. Notice that there are labels around these images, unlike using the Vision API where we had to simply upload the photos and Google will provide us with the labels. Now when you work with AutoML, you need to provide the labels. This data that's uploaded is then used to train the model that Google selects. So model training, tuning, deployment and scaling is all handled by Google. As part of the model process, you will be provided with evaluation information so that you can understand if your model is performing at a level, in other words, identifying or labeling new images properly at a level that is appropriate to your business. So now let's dive into labeling because this is so important in working with any of the AutoML services, and we'll use Vision as an example. So for Vision, in order to create any type of model, you must have 10 examples or 10 images per label, and it's recommended that you have actually 1,000 per label for production model. You can label images with a single label or more than one label. Now what kind of use case is this good for? You can see on the right here that we have some photos of buildings, and by default if you use the Vision API, these buildings would be identified with particular labels such as the location of the building, the type of the building. However, one type of label that won't be part of the default Vision API would be architecture categories. And you would find out that by simply trying that out. So if you need to label by architectural category, then your use case would be a great candidate for using Vision AutoML. So in this case, we've got different categories around architectural buildings like modern, Tudor, ranch and Victorian. So we've created a reference data and labeled it. Now, in order to do the labeling, you can either do it manually in the graphical interface, the cloud console, or in the cloud console, you can do it programmatically. There is a way to generate labels quickly for a test model, and we are going to use that in our sample. Using this method, you create a top level folder for all of your images, and then you create intermediate folders where the intermediate or child level folders, the name of the folder becomes the label for all the images in that folder. Now this is really only used to get started because it's a 30 megabyte max upload of the zip file, but it's a good way to try out the Vision AutoML without having to tediously manually label so many images. Interestingly, on the AutoML website, Google refers to the capability of human labeling. So this would be when you hire people to do the labeling as part of the data preparation. Now in the real world, I have actually done this not with particular implementation but with other type of machine learning scenarios where there was a high need for appropriately labeled information. Of course, it's extremely important to have accurate labeling in order to produce a model that is useful. This is an important step in the cost of producing this model. Now you can use Google Cloud Storage for large size files, and when you move from trying this out to a production situation, you probably would be using Google Cloud Storage rather than manually uploading data. Now just to understand the difference in using the Vision API versus AutoML, we'll continue looking at our buildings. So you can see here that of the 4 photos, the Vision API outputs labels such as property, house, architecture or home for the first image. Whereas AutoML, because we provided the labels, identifies the first image as a type modern with a probability of 0.89%. So you can see for the second image, again the Vision API identifies landmark, sky, house, building, and AutoML identifies the type as Victorian with 0.94%. So it becomes very clear in looking at this for which use cases Vision API would work versus having to label your images manually. I like to present this information in this way because I think as a use case you would want to start inputting your images in the Vision API to see what labels are produced, because if the appropriate labels are produced, then you don't have to go through the work of labeling images and then training using AutoML. So you will want to start with the Vision API first. So the first step in working with AutoML for Vision is working with your data. Now there are a couple of points to note about the data that is designed at this point to work with the API. First, data recommended by Google are images from the real world and specifically say not X-rays, hand drawings or receipts in their documentation. They also recommend high quality images, and they say that do not use any grainy images such as surveillance photos. And the maximum is 30 megabytes per image. So here are the file types that are supported. So we have JPEG, PNG, GIF, BMP, WebP, TIFF and ICO. Now let me tell you about the photos that I have prepared. You can see a folder here called Nature Photos, and I have created a zip from it. And underneath that folder, I have child folders with the intended label names. So here I have flowers, food, sky, sunset, trees and vista. And again, I'll remind you that we need to have a minimum of 10 labeled images per category or per label in order to build a basic model. So I have my zip file ready to go, and I have also provided you with the same. And now I'm going to work with it. So here I am in my GCP console, and I'm going to go ahead and navigate to the Vision API. And you'll remember that you have to explicitly enable this API. It's turned off by default. And you do that in this API section here. and we had already done this earlier. So I'm going to click on vision, and then we have our two choices. We can use a pre-trained model, the vision API, which we did earlier, or we can start using the AutoML. So let's do that. Now we are going to create a new dataset and give our dataset a name. So let's call it nature photos, and we can upload from JPEG, PNG or zip, or we can also upload a CSV file from Google Cloud Storage. And this should be a list of paths to your images on Google Cloud Server and labels if available. Now we can import the images later. Notice that you have a data preparation tip. Each label should have at least 100 images for best results. And Google's documentation is pretty inconsistent. Sometimes they say there should be at least 100 photos, and sometimes they say it should be 1000 photos. And you should read these data guidelines. Notice that you have the option for multi-label classification as well. So that is multiple labels. Note, it also says that typically it requires more training images per label to get good model results. So we are going to go ahead and select our file, and then we are going to create our dataset. Now you see that our files weren't uploaded, and you can see that the continue button is grayed out. So what we want to do here is we want to create a bucket which will be able to hold our data on Google Cloud Storage. So we set that up. The name should be all in lower cases. Capital letters do not work. The rest of the options are fine, and we just go with the default values. So we create it, and once that's done, you can see that our cloud storage path appears and the continue button can be pressed. So now you can see here that the images are being imported. It might take a couple of minutes for the zip file to be uploaded, and here you can see that it has been uploaded successfully. So I have 74 images over to the left, and all of them are labeled, and there are no unlabeled images. So here you can just go over each category and feel free to explore the data and see the images. So for the sunset category, we have images that belong to sunset. For the trees category, it has images related to trees, and so on and so forth. You can go ahead and view the label stats, and that will show you for each label how many images are present and how many are being used for training, validation and test. So again, it tells us that there should be at least 10 images for each label, and 8 are being used for training, 1 will be used for validation, and 1 will be used for test. So if we have fewer than those images, we can get pretty inaccurate results. Now we have already seen the importance of training data. The more we have it, the better it is for our models. So now this completes the data loading stage. So the next step in this process, after you have uploaded your labeled data, is to train your model. So we have explored our dataset previously, and we saw that different categories for our photos. So now let's move on to training. In addition to Google automatically selecting the most appropriate model, Google will also select the hyperparameters, and these are parameter values such as batch size, training size, and so on. So we have our input dataset, and by default this can be adjusted as shown here. 80% of the images are used for model training, 10% are used for hyperparameter tuning, and 10% are used for evaluating the model. Now these images are not used in training, and it is also called as the holdout set or test set. Now this becomes important when you are looking at the quality of the output of the model and determining whether you need to, for example, provide more sample input photos, different kinds of labels, or different kinds of photos. We'll be addressing that later, but for right now we need to train our model. So we have our model here, and then we have the images, and then the next step here that is highlighted is train. So we are just going to click on start training, and this can take a good amount of time, and what happens is that you will also get an email notification when the training process is completed. So I'll start this and then I'll pause the video, and then once it's done, I'll show you the result when the training is completed. Notice that when I click start training, it gives me a model name and then it asks me to set a node budget. You can also see the pricing options, but for this one, you can just go ahead and select one compute hour, which is free, this and this much time and this much time is enough with the data that we have. So I am going to start training, and as I said here, it gives you a warning. Training can take several hours or more depending on the compute hours you assign it. So in the meantime, you can close this window and you will be emailed once the training process is completed. So here you can see that I get an email. Now I am going back to the interface here and I'll just close this. So we can see that we have our model ID and all the details related to the model. I see that our model has an ID based on the dataset nature photos, and it has 74 images, and we can also see an average precision score of 0.60. Then we have a precision, recall and a score threshold. Now if you click on the model on the left side below datasets, it also gives you a kind of a summary. It shows that 74 images were trained, 6 labels are provided, average precision is 0.626, and then some other metrics. Now we will explore these metrics in more detail by going into the Evaluate tab, and soon we'll see that in detail. So a critical aspect of working with AutoML for vision is model evaluation. The model has to produce the correct labels. There are several ways that the model quality is measured. You remember that data is split into training, validation and test set for quality evaluation, and these metrics are presented in a nice interface. So here we have the precision recall curve, a plot of confusion matrix, etc. And to understand that, you will have to understand precision and recall. So precision is the ability for the model to predict fewer false positives. Recall is the ability of the model to predict fewer false negatives. You also use what's called the confusion matrix, and this will show the percentage of incorrect predictions, either false positives or false negatives. So if you want to learn more about these metrics and graphs, you can click the link here. Now you can also move the confidence threshold and see how it affects your precision and recall scores. You can see all the changes that are taking place on the graphs and in the metrics as I move the slider for the confidence threshold. Now of course our model hasn't performed well enough. In the confusion matrix, you can see the blue boxes with 100%, and there we get perfect classifications. And then we also have grey boxes with 100% that are missed classifications. So since we had chosen a single label classification and not multi-label classification, thus the other boxes are empty. Now if you want to see the counts, there is a toggle button on the right side, and that will provide you with the item counts instead of percentages. You can also download the confusion matrix as a CSV file. Now if you want to see each class separately, what you can do is just click on any one of the labels on the left side, say for example flowers, and that will show you the performance for that individual class. Again, you can play with the confidence threshold and you can check other categories like food, etc. It also provides you with false positives, and it provides us with what should have been predicted and the score it got currently. And again, we have a small amount of data, so you don't have confidence in the model's performance. In production, you would actually need exponentially more labeled images. Now, in order to work with this, what we could do is just try out a prediction. But before we do that, I just want to go back and talk about the ways we can improve the accuracy of this model. So according to the documentation, there are several ways that you can improve the model quality. First, of course, you want to add more data, and then you want to review the image labels and you want to update them as needed. Also, you can add more types of images for each label type, and they may be wide angle shots, close up shots, etc. There should be diversity in the data. So now let's look at the predictions and we'll deploy the model here. Now once we have created a model, we have trained it, we have evaluated it, let's use it. The easiest way to try out this is to use the predict button. So this is very similar to using the Vision API, in that which we had an endpoint and you can simply upload an image, and then there's a REST API or a Python API, and then we can look at the predictions. Of course, labels here we would expect to have something to do with the labeled data that we presented. So let's try it out. So to test the model, we will have to deploy it, and you can do that free of cost, but you can also check the pricing guide. And we are going to deploy the model on one node, and we click deploy. You will also get an email saying that the model has been deployed. So now we need to upload our images, and I have created a folder called Photos Direct, and purposely I have picked some photos that I think should be predicted correctly, and there will be some photos which are not predicted correctly. So let's try this out. So once the images are uploaded, the predictions will start coming out. You can see that the image Bitter Bolin has some food and a glass of soda. So this has been predicted as food, and that's correct. Now we have an arm wrestling image in the form of a statue, but we have not got a prediction for it as yet. Now we see this blue martini which has got a prediction of food with a score of 0.96. So that's fine. Now we have this first program image which didn't get a prediction as yet. We also have this sunset image which got a prediction of sunset with a confidence of 0.66. Now for the arm wrestling, it wasn't able to show a prediction, and it shows us no objects. So again, what I am trying to demonstrate here is that it goes to the old metaphor of saying what you put in is what you get. So the quality of information is heavily based on the training images. And again, just to refresh what we had here, for example, we had a good result with food. What happens in this type of modeling is that the closer that you have a match, the higher the likelihood of prediction. Google actually says that this is designed to work in situations that mimic human ability to visualize. So I'm sure they will evolve this API and there will be additional capabilities. But I think it's very important to understand what it's designed to do and what it's designed not to do. So to summarize this session, where we have covered both AutoML and we have referred to APIs or endpoints, you want to use the APIs or endpoints, send data, picture, videos, text to the endpoint, and then the API would return labels. And you can also get likelihoods as well, like percentage of likelihood if there is a cat present in the picture, for example. So you have got to authenticate and you pay by the invocation. But for AutoML services, you create the labels and label your data, and the quality of output is heavily dependent on the quality of the data and quality of the labels associated. You send that labeled data, pictures, text, video to an endpoint, and Google creates the model training, and they tune the hyperparameters and present you with numeric evaluation. As you saw though in the earlier section, I highly recommend that you manually test, as this is a relatively new service and you want to understand the quality. Also, just to reiterate that you may need to provide more labeled data to get a optimum model performance, and then you can predict using that model endpoint. So with this, we conclude our session on AutoML.